Okay, so let's take a look at how to verify that a given formula is in fact a solution to a differential equation. So just like with integrals, finding the solution can be tough, right? Integration is hard, quite often. But verifying that a solution is in fact correct, this just involves substitution. It just involves differentiation. And differentiation is largely a mechanical procedure. You just apply the techniques, and if you follow the rules, the answer falls out. It doesn't require the creativity that solving integrals does. So let's look at some example problems here. And so for each one of these, we're given a formula and a corresponding differential equation to check to see that it satisfies. And the way that I usually do this is, well, what you do is you're going to be substituting the given formula into the differential equation. And you just want to make sure that it satisfies it. So in other words, that you come up with something that's true. So let's see. For this one here, I can begin by just taking the first derivative. So I've got the first derivative appearing in the differential equation. So I take the first derivative of my function. So this is going to be by chain rule, the same function as before, times the derivative of the exponent. And so that's going to be c e to the minus x squared times minus 2x. And if I pull the minus 2x out front, I have c e to the minus x squared. And then I recognize from the given function right here that this part, is in fact equal to y. So that means I can rewrite this as minus 2xy. So going from left to right, I have y prime equals minus 2xy. And I have recovered the ODE that I was supposed to get. Let's look at another example. So this one says, verify that x squared plus y squared equals 9 implicitly defines a solution of this ODE y prime equals minus x over y. So the implicitly here is your indication that you're going to need to do implicit differentiation. So in other words, you think of this as x squared plus y of x squared equals 9 because y depends on x. And so then when you differentiate both sides of this equality, you remember that you need to use the chain rule for this y term right here because y depends on x. So d dx of x squared is 2x, and then d dx squared of y squared is 2y times dy dx by chain rule, and then the derivative of 9 is just 0. So we can tidy this up a bit. I can cancel off the 2's, and then I can rewrite this. Let's see, so x equals minus y prime by subtracting that term over to the right hand side. And then if I divide the minus y over to the left, it looks like minus x over y equals y prime. And that is exactly the same thing that we were supposed to get. So in other words, these are the same. Let's do one more. So I'm going to take this function here, y equals c minus x to the negative 1, and to substitute it in right here, I'm going to need to differentiate. So I take y prime equals minus c minus x to the negative 2 times by chain rule the derivative of c minus x. So that's going to be a negative 1 coming from this part right here. So now I have two factors of negative 1, c minus x to the negative 2, which I can rewrite as 1 over c minus x quantity squared, because I notice that this is actually my y from the very beginning. So this is y squared. And now from left to right, I have y prime equals y squared, and that verifies my differential equation. Hooray. Okay, and then this one actually asks for a part B, so I guess this was the solution to part A. And for the solution to part B here, now I'm going to set x equal to 1, y equal to 2 in my equation, and that's because that's what this says to do right here. I've got x is equal to 1 and y is equal to 2. So let's see what we get. So from, let's see, so I'm going to have 2 is equal to y of 1 is equal to, and now I take my differential equation, or sorry, not my differential equation, my solution, and I have 1 over c minus 1 because we're setting x equal to 1. Now I need to solve this for c, so I'm going to cross multiply, and I have 2c minus 2 on the left is equal to 1, and then I can take this guy and hop him over to the other side by adding by 2, and so it looks like 2c is equal to, and then, sorry, so I'm going to add 2 to that, so I'll get 3, and so then I have c equals 3 halves, and then that tells me that my particular solution is going to be y equals 3 halves minus x in the denominator. And so if you like, maybe this is just a matter of artistic preference, but I kind of like to get rid of the fraction, so I would multiply this by 2 over 2, and like I said, this is totally optional, and it would look like 2 over 3 minus x, and that's how I would present my solution to this problem.